Okay, let's go ahead and take time to do the lesson, and you can finish up that mural drawing as part of the assignment. Alright, so using the idea of similar figures, you can, as we're trying there with the mural, trying to enlarge it or reduce it. The idea of perspective ties into our lesson today, where in order to make it look close, you're drawing something big, but then the same thing further away would be smaller. When you do perspective, in order to line things up to make a parallel, there really is some of the theorems that we're talking about today would be a way to figure out what measurements you should have with things apart in order to make them look parallel. I found a couple pictures that I thought were a good example of perspective. This is just a scene, I think, like New York City idea. It says, compare the size of the taxis. You see the taxis close are bigger, further away they're smaller. And I'm sure that you've noticed this in real life, but maybe not really mentally thought about some mathematics that could be involved in why that's so. I drew some lines in there now, like taking the edges of the streets or the top edges of the building, and when I traced all of those, notice how they come to one point way back there in the middle. That would be your vanishing point. It would be a one-point perspective kind of picture. In art, usually in the middle school, students tell me that they had to do 1 point or 2 point perspective. Do you remember doing that in your art class? Okay, that's the idea of getting things the right size. And this one had a good perspective by, again, went on the edges of some of those matching things. Kind of cool. I think that reminds me of probably like a hotel, but someplace that has balconies, kind of old style. And this one was an interesting kind of perspective. Not a monkey, but to make that look that way, how did they set it up? She's actually standing further back and just positioned correctly so that they touch there. So interesting way to make the perspective look. Okay. So here's a theorem that ties into the idea of perspective and how long the segments should be. This is called the triangle proportionality theorem, and it's important in making accurate perspective drawings. It says if a line is parallel to a side of a triangle, it's going to intersect the other two sides. So this extra line in the triangle, parallel to that side, says it divides those sides proportionally. Now, we looked at a mid-segment, and this is not necessarily a mid-segment because it's not, E is not really a midpoint of that side, and F is not really a midpoint of the other, but this is a special case, or let's see, I should say the mid-segment's a special case of this theorem. If a line parallel to a side of a triangle intersects the other two sides, then it divides those sides proportionally. And as we're doing in our chapter, proportionally means the ratios are equal. So as we try and apply this one, if we have the hypothesis situation, triangle with the extra parallel, then look at the ratio that they're saying is the same. AE and EB. So those two pieces that the parallel intersects, the ratio of those two is the same as on the other side, AF and FC. So it's not the little triangle compared to the big triangle that we've been doing in the last few days. This is a little bit different version. Ready for an example? Okay, so let's find the length of PN. Do we have the triangle with the extra parallel? Yes, we do. The theorem said you can do a ratio with the segments where that line intersects. So you can either go, let's talk about the right-hand side. Either 2 over 5 or 5 over 2, whichever preference you have. Then set that equal to 3 over x, because that's what we're trying to find. So either 2 over 5 equals 3 over x, or completely upside upside down. Cross multiply. 15 divided by 2 is 7.5. GN would be 7.5. Could you do this problem using the triangles? You could. Let me just have you do a little comparison. If we did the triangles, we would have, let's see, 5 and 7. We would have x and x plus 3. Right? So then you could do 5 over 7 equals x over x plus 3 and cross multiply. If you solve that correctly, you'll still get 7.5. But I think the one that we set up following our new theorem is simpler to solve, but it could be done either way. Let's have you grab your marker board for the next one. I want you to find US, check of understanding. What's the length of US? These will not always be whole numbers or integers. So be prepared for some decimals or fractions. Ratios that you're using, 14 over x equals 10 over 4. Maybe 4 over 10 equals x over 14. Different ways you could set that up. And could you reduce the 4 and the 10 to 2/5 before you cross multiply? Sure, that's going to just produce smaller numbers when you cross multiply. Okay, the converse of that, we'll use the marker board again, so don't put it completely away. The converse is how you will decide if the lines are parallel. So if a line divides two sides of the triangle proportionally, then it is parallel to the third side. So if it divides proportionally, so if the ratios are the same, then we can conclude that line EF and BC are parallel. So in this kind of a problem, we're going to have all 4 number lengths, and the question's going to ask, is line EF parallel to BC? So you'll test the ratios, see if they're equal, and that'll tell you yes or no if the parallel is there. An example of that. This one. Okay, verify that DE is parallel to BC. So let's check the ratios. So we could compare 10 to, which one does the theorem say to use? 10 to 15 or 8? 15. Okay, I have students that like to put it over 8. Now, it's 10 to 15, and then from the other side, the same sections would be 8 and 12. Reduce those to see if the ratios are the same. So 10 and 15 can reduce to be 2/3. 8 over 12 divided by 4 would be 2/3 also. Okay, so those two ratios are equal. The sides are in proportion, so the conclusion then by that converse is that the lines are parallel. So here's my complete details. So since those ratios are equal, the lines are parallel by the converse of the triangle proportionality. Okay, one for you to try. I wrote some of the measurements off to the side, so make sure you're using the right numbers. Check to see if the sides are divided proportionally. That will tell you whether the line is really parallel or not. Reduce the ratios to show me that they're the same, or if they're the same. Terms of reduced. Well, what segments are you comparing? Okay, AC was a total of 36. That's the whole thing. That's 36. And this whole thing is 27. So what did the theorem say to compare? Should you put 20 over 36? No, you should put 20 over 16 that you got by subtracting, and 15 over 12, or else reversed. So just be careful which ones you're using. I did 20 over 16 and 15 over 12. They were both 5 to 4, so that fit the hypothesis. So the conclusion, the lines are parallel. Thumbs up or down? Did you do the correct segments? All right, let's go to the two transversal proportionality theorem. I think I just did a couple of examples on this one. The two transversal proportionality. So this one has 3 or more parallel lines, and they're intersecting 2 transversals. So the AE line is a transversal, the BF line is also a transversal. If you would, in your mind, extend those 2 transversals up, you'll notice you really would form a triangle. So this is kind of an extension of the theorem we were just looking at, where you would have multiple parallels with the triangle involved. So if 3 or more parallel lines intersect 2 transversals, then they divide the transversals proportionally. So about the same thing as the triangle theorem we're looking at, but it just doesn't close. So again, you can make a ratio, AC and CE, BD and DF. Those ratios would have to be the same, or will be the same. If we put another parallel in, just to clarify, let's call that M and P. You could make a ratio out of AC and EM. They don't have to be just consecutive segments. But then your ratio from the other would be using BD and FP. just make sure you use the same sections, and the theorems ratios would be the same also. Finishing up notes. This picture is an art application of the theorem. Okay, we've got trees. I got 4 trees. I want those trees to be standing parallel to each other. Got some measurements figured out, but I don't know exactly where to position M. So I need to know LM's distance so that they really end up parallel. I also need MN's length so that I can accurately make those parallel. So what length would those be? We're trying to find LM. X where you can see it there. What ratios could we use? H? 4.5 over 2.6, okay. And then, not X over 4.9. Which one did you give me first up here? You gave me the 4.5. So from that section, you'd need the 4.9 on top. Okay. So she could do 4.5 over 2.6 equals 4.9 over X, or the complete reciprocal of that. And what's that come out to be? 4.5 over 2.6, 4.9 over X. What is X to the nearest 10th? Some of you are waiting for the rest of us. I need you to participate. Cross multiply. Any question what I set up to cross multiply? Megan, what'd you get? 2.8. 2.8. Okay, now you set up something to find MN. I'll call that Y instead of X. So figure out what Y is for me. Have more than one option what to use to set it up. We'll see if all of them produce the same answer. Okay, answers? 4.4? 4.4? Okay. Which numbers did you use? Did anyone use the 2.8? Okay, some of you did. Okay, anyone not use the 2.8? Everyone did. That's why we're all agreeing. I was going to suggest that you don't use the 2.8 because didn't we round that? So we, no? When you calculated this, you didn't have to round it? Okay, so you did round it. You cut off some of the decimal. So this 2.8 isn't most accurate. So you're probably getting a little bit different answer than if you had set it up without. How would you set it up without? You could do, yeah, on this side, you could use the 4.9 and the Y. And then you would use 4.5 and 4.1. You might just cross multiply that, see if that's the same answer that you got. Does it come out the same on this problem or different. There will be some times that would be different. Is that the case here? Brenda, does it end up the same as what we had before? It would round to 4.5. Okay, so that is an example where you'd get a different answer. So as we're going through, it probably would be best to try and use original information rather than something we've calculated, especially if we had to round that. That's the two transversal proportionality. I think we have one more. The triangle angle bisector theorem. This says an angle bisector of a triangle divides the opposite side into two segments whose lengths are proportional to the lengths of the other two sides, which sounds kind of confusing. I want to see if we can create this on either GeoGebra or Geometry Pad. So once you get the notes, let's grab your device and see if we can make a triangle. Put an angle bisector in there. And then I'm going to be interested in the lengths of BD and BC, BD and DC in this picture. Either try GeoGebra or Geometry Pad. I'm sure we can do it in GeoGebra. I'm not positive if we can get the measurements in Geometry Pad or not. But you would need a triangle. Doesn't really matter what kind you start with. But then you need to bisect one of the angles of the triangle. Tell it to do angle bisector or perpendicular? I don't want perpendicular, I want angle bisector. Down towards the bottom there. So you probably want to do it like that. Okay, once you get your picture, the measurements that we're interested in is the two sides AB and AC, because we're going to make a ratio out of those. And then we also need, to this point D, I need DB and I need DC. See if you can measure those four different things. That's the part that I'm not sure we can do in Geometry Pad. Let's try. There should be a choice, yeah, bisecting an angle. Bisecting the angle. Do you have to touch the three corner points? Let's pick angle bisector. There you go. So select the points. That one. Did that bisect that angle maybe? Instead of the one we were thinking? It looks like it anyway. What's it doing? I don't know what it's doing. Is that you might try and touch those and delete them, like select it. Okay, but now you need your angle bisector back. You might pick it, make sure that we've got the right thing. That point, that point. You might have to get a point at that corner. And you can maybe do intersect. Oh, you started completely off. Yeah, draw a triangle again, I guess. I've never seen it done that way. That's cool. Try and do an angle bisector. Is it working to create what we want? You might have to put a point where that bisector intersects the triangle. You might have to have a point at that intersection in order to do some measuring. Looks like we got the picture. Let's put a point, intersect that line and that triangle. That line. Touch that side. So that's got to be. So now you should be able to do some measuring. Can you measure the segments? I think you have to do like distance and length. If you're in GeoGebra and not finding the measurements, we did like the one, let's see, angle. It's the 1, 2, 3, 4, 5, 6, 7, 8. The eighth icon over, if you click that one on GeoGebra, there's a choice distance and length. That can help you measure the segments. Okay, now what I want you to explore, students think that that angle bisector always is the midpoint. So I want you to stretch that triangle around, pick corners of it, and look to see what those measurements are like. D is not a midpoint. So I'll select, like with the first icon off to the left. Then you can grab a corner. Some of the corners will move, some won't. So you have to pick which one will let you move. Because I think a lot of your triangles that I'm glancing at, they kind of look isosceles. So I want you to stretch it and make sure that you see it's, even when it bisects the angle, it's not going to the midpoint. Doesn't look right. If you would connect segment. Now, did you create D? Oh, okay, that's probably what our issue is. Did you make D as an angle bisector? Just randomly put it there? Okay, so let's try and get rid of that. We want an actual angle bisector. Angle bisector. Then you have to select 3 points. So maybe go B, A, C. It bisected it. Now you can tell it to put a point there. Now it's an accurate point. Stretch and see. Okay, am I getting you to realize that that's not always an angle bisector? Or, excuse me, the angle bisector is not going to a midpoint? Okay, now the theorem is saying it's going to divide those sides proportionally. So stop your picture somewhere so that you've got some actual measurements. And I need to hear some numbers. Got some measurements? Okay, can you give me the sides of the triangle? Or is it not good? These are huge numbers? So maybe it'd be better if I try just my example. Oh yeah, I don't want the angles, I want the segments. Okay. Something like one side might be 40 and the other 32. Okay, so I guess let's look at my example. That might be better than using the numbers that you've got. Okay, what ratios would be equal here? Well, if I compare the 40 and the 32, that's going to be in the same ratio as segments where that angle bisector goes. Which one do I put on top is usually the question. Okay, well, if you took the 40 first, you're going to take the x plus 5 that it's adjacent to first. So if I did 40 over 32, then x plus 5 over x minus 2. Understand my setup. All right, cross multiplying it, I think we can handle that part. Okay, so let's look at another one, how you would set it up. I'll show that solution. When you did the distributing and solved, x was 30. So if x was 30, notice this length would be 28, and this one would be 35. The longer piece is by the longer side of the triangle, the shorter piece by the shorter side of the triangle. Let's try another one. Okay, so how would you do this one that would be an example of what's on the homework? What ratios have to be the same? Let's make one out of these two segments. You want me to go 4.5 over y minus 2, or y over 2, is that okay? 4.5 over y divided by 2 has to equal the same as 8 over y minus 2. The consecutive pieces or adjacent pieces are the ones that go in the same spots. This one you probably just want to practice the solving. 4.5 times y minus 2 and 8 times y over 2. We've been working on the distributing. Hopefully that side's not a problem. 8 times y over 2. 8y divided by 2, which is 4y. So I'm just going to put 4y here. Kenna?
So like putting that word, we get 4.5 over y equals y minus 2.
Okay, 4.5 and y minus 2 over 8. Okay, actually, no, because the setup that I have, let's go back to the theorem, I guess. Look at the theorem. Doesn't it say AB over AC and BD over DC? But no, it will matter because when I cross multiply what you said, notice I'm multiplying different things than what the theorem really tells me. The only change could have been the y over 2 could be on top, but then the y minus 2 has to go on top to match with it.
So you couldn't do 8 over 4.5 over 12 minus 2 over y.
Minus 2 over y.
Did you not do that? I mean, it's the same thing. It's just
That's the same cross multiplying. That one would work. It doesn't follow the theorem, but it would work. Because when you cross multiply this, it is the same as what I've got. So there are some you can do different. I would try and use the segments like we had. But there are some different versions anyway. Okay, your mural picture, I'm going to try a little more drawing on that. I'll get that finished up. And then a little bit out of the book, I didn't go too crazy. Page 484. It doesn't look like near as much when you go one through something. And do that mural. We do have a quiz tomorrow, so I'm going to give you some optional quiz problems. The quiz I'm doing 7-1, 2, and 3, and 6. These should all be listed in your backpack. of you that are coming in to take the quiz early, maybe at least glance at those and see some of the types of problems that are on that quiz for you. Our solution up here was 18.